Hello, Algebra 2. This week our lesson objective is to teach you how to solve log equations. There's a couple of different strategies that we'll be using. One will be to restate the problem in its exponential form. The other will be using something called the one-to-one property. We'll explain what that is when we get to it. And then lastly, solving by graphing, a strategy that we've used plenty of other times to solve equations this year. So here we go. Let's dive into it. Before we start, let's take a second and make sure you understand what we mean by a log equation, and we'll do this by drawing some parallels here. On the left, you have what I hope you recognize as generic linear function, y equals mx plus b. If we wanted to give you a specific example to make it a little more clear, we could say y equals 2x plus 1. So that's a linear function with a slope of 2 and a y-intercept of 1. So first of all, if we took a linear function and we plugged in a value for x and asked you to solve for y, technically, yes, that's a linear equation, and we are asking you to solve for y, but really that's not much of an equation to solve. That's really just an exercise in the order of operations. I hope you realize that, to get the answer, first you have to multiply, so that's equal to 6, and then you have to add 1, so that's equal to 7. So you might look at that and say, yes, it's a linear equation, but it's really not much of one. It's just an exercise in order of operations. So the same thing is true with log functions. On the right-hand side, there's the generic form of any log function, y equals log base b of x. Again, if we wanted to make this more specific to eliminate a little confusion, we could say, all right, let's consider log base 2. So now we have y equals log base 2 of x. And similar to linear functions, when we give you the x value and ask you to find the y, it's really not much of an equation to solve. It's more just a exercise in order of operations. This one's not so much a question of order of operations, it's just a question of, do you understand the operation? Do you understand what that means? Well, that's log base 2 of 8, which in our prior work on logarithms, I hope you understand that that's asking the question, 2 to what power is equal to 8? So really, that expression is just a very convoluted way of writing the number 3. So this is really not a log equation that needs to be solved. It's just a question of evaluating the logarithm. So continuing with the analogy, here's really a better example of what it means to solve an equation. On the left-hand side, we have the same linear function that we were using before, but instead of giving you the x value and asking you to solve for y, we're giving you the y value and asking you to solve for x. Now you have an actual equation that requires some work to solve, and hopefully you understand how to isolate the variable. So you follow the order of operations and you do what's necessary to get the x by itself. And now you've really got an equation that had to be solved. So similar situation with log equations. There's the same log function, log base 2, except now instead of giving you the x value, we're giving you the y value. So the question is, how do you isolate this variable? And we'll talk about that when we get more into the detail of how you solve log equations. But this is really a more typical example of the kind of problems you're going to have to solve, at least one of the kinds of problems you're going to have to solve. Before we move forward and talk more about those techniques, I'm going to clear the slide so that we can just remind you of one other thing. So as we mentioned in the start of the presentation, another way we have sometimes solved equations is by graphing. So we would just remind you that if I wanted to solve by graphing, first of all, on the left-hand side, here is the graph of the linear function y equals 2x plus 1. And one way to solve this would be by graphing. You can see that we're giving you a y value of 9 well, here's a y value of 9. And so if we wanted to solve that, that's the point where y equals 9. And so we would just have to look at it and see, well, what's the corresponding x value? Well, the same is true, of course, with log functions. Here's the equation y equals log base 2 of x. And we're giving you a y value of -1. So if you look on the graph, you can see, well, here's the point where y is -1. And now the question is, what is the corresponding x value? You can see that you have the usual problem of solving by graphing. This is something we've encountered before. If the answer on the graph is not a nice round number, then it becomes a little difficult to see exactly what the answer is. Maybe you know what the answer is, but we just want to remind you that solving by graphing is still an option. Of course, it's always still subject to the usual limitations. And we'll say some more about solving by graphing a little bit later. Okay, so I think the easiest way to explain how you should solve log equations is just by diving in and showing you some examples. So here are the 6 examples that we are going to use in this slideshow to illustrate the different techniques you need to use and some of the things you need to be careful with. So before we look at each of these problems more closely, just want to point out something that you might have already noticed. Notice that the first 3 problems only involve one logarithm, and then the last 3 problems, excuse me, the first 4 problems involve one logarithm. But the last 2 problems have 2 logarithms. So you have a logarithm on one side of the equal sign or logarithms on both sides of the equal sign. And that's an important thing to notice. It's going to affect our strategy. So you might want to pay attention to that whenever you see a problem. Okay, so now we'll take a closer look at each of these problems. Here are the first 2 of those 6 problems. As we noted, these problems only have a single logarithm. The first problem, we just want to remind you once again, technically I don't even really consider that a log equation because log base 4 of 8, that's just a logarithm that we need you to evaluate. That's asking the question 4 to what power is equal to 8. Now, that particular logarithm is a little tricky. If you take a second to just think about this, we're saying 4 to what power equals 8. Well, 4 to the first power is 4, and 4 squared is 16, so this must be some number between 1 and 2. So you might be wondering, how can I answer that question? Well, one way to answer that is with common bases. This is something we taught you back in the unit on exponentials. You could write 4 as 2 squared, and you can write 8 as 2 to the third power. Using exponent properties, this is 2 to the 2x, and this is 2 cubed. And now that I have a common base, I can see that, okay, well, if I just ignore the base, I know 2x is equal to 3, and so that means x must be 3/2. The trick here is that's not the answer to the equation, that's just the answer to the logarithm. So 3/2 is just this logarithm. So if I clear the board, this logarithm is really just 3/2. Now, that's the equation you're solving, and you don't really need to do anything to solve a log equation here. You just had to evaluate the logarithm log base 4 of 8. So this is, in my book, this is technically not even a log equation. So that would be 7/2. Problem 2 is really truly a log equation. So we have a single logarithm, and notice that the variable is actually inside the logarithm. That's what makes a log equation. It's having a variable inside the logarithm. So how do you go about solving an equation with a single logarithm? The strategy that we mentioned in the lesson objectives, one of the strategies, is to rewrite it in its exponential form. This is something that we taught you early on in the unit when we explained what a logarithm is. That logarithm is equivalent to the statement 3 to the 0 power is equal to x. So you can see if you just rewrite the logarithm in its exponential form, you've isolated the variable. 3 to the 0 power is 1, and so we know the answer is x equals 1. Okay, so here's two more examples of log equations that have a single logarithm. Notice that in both of these problems, the variable is inside the logarithm, so these truly are log equations. As we explained, the strategy when you have a single logarithm is going to be to rewrite it in its exponential form. So problem 3, that logarithm is equivalent to saying 4 to the negative 2 power is equal to x. In case you don't remember, negative exponents just mean 1 over. So that's really 1 over 4 squared, which means the answer is 1/16. And this other problem, problem 4, if I rewrite it in its exponential form, that is saying 3 to the 3rd power is x plus 5. 3 to the 3rd power is 3 times 3 times 3, which is 27. And now I have to do just one more step to isolate the variable, so I got to move the 5. And now I've got the variable isolated, and there's your answer. Okay, so our last two examples, now we have equations with logarithms on both sides. And here's where we want to use what's called the one-to-one property. So the one-to-one property is really is a name for something that I guess we haven't discussed before, although we technically have used this property before, we just didn't talk about it. We didn't call it that name. So remember back when we were solving exponentials, in fact, we did this earlier in the presentation. I think, I don't remember if I had this exactly right, but we had something like 4 to the x is equal to 8. Well, we use this method that we called common bases. We had to rewrite that 4 like it was 2 squared, and that allowed us to do this. And when you have a common base, then you can just ignore the base and you end up solving something like that. Well, a similar type of thing can be done with logarithms. This is really an example of what we call the one-to-one property, and we're not going to go into the details of what the one-to-one property means. That's a little hard to explain without being able to teach a lesson face-to-face. We're just going to draw a parallel and say, well, imagine you had log base 2 of A and you had log base 2 of B. Well, if those are both log base 2, kind of like these were both exponents with a base of 2, can't you just cross these out and say A has to equal B? And that's really what we mean by the one-to-one property. It's a lot like solving exponentials with a common base. So clearing the board here, if you look at problem 5, you will notice that both of these are log base 2. So it should stand to reason that we can just ignore the logarithm. And if this equation is true, then x has to equal 2x minus 4. And that's all we mean by the one-to-one property. Okay, well, if you're going to solve this equation, we could subtract 2x from both sides. And now we get negative x is equal to negative 4. And if you multiply both sides by negative 1, then you'll have x is equal to 4. And that's the solution. Now, if you try that same method on problem 6, notice these are both logarithms of base 1/2. You should be able to cancel the logarithm. So x minus 3 should be equal to 2x plus 1. If I wanted to solve for x, I would subtract x from both sides. And now I have negative 3 is x plus 1. And then I would subtract 1 from both sides, and now I get x equals negative 4. Well, there's just one small problem here. So I'm going to clear the screen, but first let's note these answers. So problem 5, the answer is positive 4. Problem 6, the answer is negative 4. Let's clear the screen and take a minute to think about those answers. Okay, so here we said it was x equals 4, and here we said it was x equals negative 4. Well, let's test that answer on problem 5. You're saying that log base 2 of 4 equals log base 2 of 2 times 4 minus 4. Now, 2 times 4 is 8, and 8 minus 4 is 4. So if you look at what you have here, I don't even have to evaluate the logarithm. I can just look at that and say, well, yeah, that's true. Log base 2 of 4 equals log base 2 of 4. So that answer checks out. Now here comes the problem. If you, on number 6, if you plug in the answer, you get log base 1/2 of negative 4 minus 3, and log base 1/2 of 2 times negative 4. Sorry, this is getting a little hard to squeeze in here. Okay, negative 4 minus 3, this is log base 1/2 of negative 7. And the other side is also log base 1/2 of 2 times negative 4 is negative 8, plus 1 is also negative 7. Now, at first glance, it looks like, well, number 6 is right. Just like you said number 5 was right. You have log base 1/2 of negative 7 equals log base 1/2 of negative 7. Those two answers match, don't they? Well, the only problem is, what's log base 1/2 of negative 7? You have to remember that you can't take the logarithm of negative 7. So log base 1/2 of negative 7 doesn't exist. This is not valid because that logarithm doesn't exist. Going back to example 5, what's log base 2 of 4? Well, this is asking 2 to what power equals 4? Well, that's 2. So in problem 5, what you're saying is 2 equals 2. And that's a true statement. But on problem 6, there is no log base 1/2 of negative 7. It's not possible. If we wanted to take one more look at this to try to convince you that number 6 really doesn't have an answer, we remind you of, let's think about solving by graphing, something that we mentioned in the beginning. So problem 5, you can see I used a graphing calculator and I graphed log base 2 of x, that's the blue graph, and then I graphed log base 2 of 2x minus 4, that's the red graph. And then I found the point of intersection. You can see the two graphs on the lower portion of the screen. And you can see I found the point of intersection, and the calculator confirms that the graphs intersect when x is equal to 4, which is exactly the answer we got. If I try to graph the functions on number 6, here the blue graph is log base 1/2 x minus 3. The red graph is log base 1/2 2x plus 1. I've adjusted the window here. You can see this is going from x equals -2 to x equals positive 18. The blue graph and the red graph do not intersect. Now, maybe you think that if you keep going farther to the right, the graphs will intersect. They don't. You can take my word for it, or you can play with a graphing calculator on your own. But trust me, no matter how far you go to the right, these two graphs never cross. And that's another representation of why there is no solution. So the thing you've got to be careful with here when you use the one-to-one property is you have to be mindful of the fact that logarithms have restricted domains. Remember, logarithms don't have domains of all real numbers. They typically have domains only from wherever the asymptote is to one side. So if you get an answer that's on the wrong side of the asymptote, that can't be a valid answer. If you take a look at these graphs, you can see that the blue graph has an asymptote at 3. And I hope that makes sense to you because you understand transformations. The calculator, sorry, I was going to draw this in the right color. The calculator doesn't show you the asymptote, but the asymptote on the blue graph is at 3. And the asymptote on the red graph, now this one's a little tricky because it involves something we haven't talked about in graphing. That's a horizontal dilation. This asymptote is at -1/2. So the blue graph only exists to the right of 3. The red graph only exists to the right of -1/2. We were claiming that the answer was x equals -4. Well, you couldn't possibly have an answer like that because it's on the wrong side of the asymptotes. So I hope that makes sense as to why that equation has no solution, and I hope it points out something you got to be careful with. Should only be a problem when you're solving with the one-to-one property. When you solve with the one-to-one property, you need to be careful and make sure that you plug your answer into the original equation and make sure it works. And when we say make sure it works, that don't just check that you're getting the same logarithm on both sides of the equation. You need to make sure you're getting a logarithm that can actually be evaluated. So that wraps up our objectives. You have 3 different strategies that you need to consider here. The first strategy only applies when you have an equation with a single logarithm. If you have an equation with a single logarithm, the way to solve it is to restate it in its exponential form. But when you have an equation with 2 logarithms, then you're going to want to use the one-to-one property, which basically means if the bases of the logarithms match, then you should be able to ignore the logarithm, so to speak, and just solve the equation. Be careful though, and make sure you check your answer. Make sure that it is a valid answer and that you're not violating the domain restrictions on the log functions. And then the last thing that we talked a little bit about is don't forget you can always solve by graphing. Graphing both sides of the equation and finding the point of intersection is a valid way of solving sometimes. Okay, so to check your understanding, we've got 6 problems that we want you to try. These 6 problems all appear in an assessment that's in It's Learning. But I put them here on the screen because I want to just remind you once again of what you should take away from this before you try this assessment. So notice problems 1, 2, and 3. Those are all problems with single logarithms, so you should hopefully be able to solve those by just restating it in its exponential form. Some of you might need to go back and refresh your memory on what does a negative exponent mean, what does a fractional exponent mean. Provided you remember those things, you should be able to get the answer to 1, 2, and 3 just by restating it. Question 4 and 5, now you have equations with 2 logarithms. They're logarithms with matching bases, and that means you should be able to use the one-to-one property. In other words, just ignore the logarithm and solve the equation. But don't forget, make sure you check your answer and make sure it's an acceptable answer. In other words, it doesn't violate the domain restriction of the log function. So be careful with that on problems 4 and problems 5. Now, problem 6. Notice this is an equation with two logarithms, but they're not logarithms of the same base. So this is something we'll talk some more about next week. If you don't have the same base, can you use the one-to-one property? Well, you can't. The one-to-one property, remember going back to the unit on exponentials, you had to have a common base to be able to ignore the base. And the same is true with logarithms. So if the logarithms do not have the same base, you cannot just ignore the logarithm. You cannot use the one-to-one property. So how would you go about solving an equation like number 6? Well, we'll remind you that you can always solve by graphing. So if you need to solve by graphing, solve by graphing. I'd just like to point out that these are functions you should be able to graph without a graphing calculator. But if you feel like you need to use a calculator, feel free to use a calculator to help you with the graphing. I will also tell you that next week when we talk about this problem, we're going to talk about this exact problem next week. There is a way to solve this without graphing and without using a graphing calculator. But that's just a little spoiler alert for something that's coming next week. So good luck, and go log into It's Learning, and you should find the assessment where you can enter your answer for these 6 problems.